cable segregation for operational integrity, and EMCs. Instrument signal cables must be physically segregated according to voltage class, safety classification, and system criticality to ensure signal clarity, safety compliance, and electromagnetic compatibility. Redundant cables for critical systems, such as depressurization circuits or dual-path control systems, must be routed independently along separate paths, both in field and control areas, to preserve functional reliability in the event of localized damage. Cables carrying intrinsically safe IS signals must be segregated from non-IS circuits per IEC 6079-14 requirements. Signal level class 5 cables, e.g. solenoids or power circuits, require physical separation from lower level signal classes 1 to 4 due to their higher energy content and greater electromagnetic emission potential. However, pneumatic tubing and fiber optic cables, signal class 6, may be bundled with any electric cable types due to their non-conductive or non-interfering nature. Segregation supports both operational and maintenance convenience. Field-level segregation may be driven by system grouping, e.g. gas detection, process analyzers, instrumentation for specific units, while control room segregation ensures logical organization across marshalling panels, termination blocks, and system cabinets. Routing design for accessibility, safety, and EMC optimization. Effective cable routing integrates structural availability, physical protection, fire zone avoidance, and maintenance accessibility. Single-core SIG cables are routed from field devices to junction boxes via dedicated supports such as trays, trunking, steel angles, or beams. Conduits are not recommended due to their limitations in ventilation, accessibility, and thermal expansion. Above-ground routing must avoid interference with equipment access points, high-temperature surfaces, sample stations, and drain or vent lines. Routing near earthed steel structures or piping is encouraged to reduce electromagnetic exposure and enhance shielding effectiveness. Riser points exposed to vehicular or equipment traffic or mechanical protection structures to prevent impact damage. Underground multi-core cable routing is preferred where feasible, as it provides superior protection against mechanical damage, UV degradation, and fire. Underground routes must maintain defined separation from power or lighting cables, typically a minimum horizontal distance of 0.3 meters, and right-angle crossings are mandated for EM immunity. Separation from buried hot pipes must account for thermal degradation, calculated as 0.2 meters plus 0.1 meters per 100 degrees Celsius of pipe surface temperature. All routing layouts must prioritize access for cable pulling, ensure bending radii comply with manufacturer's specifications, and support future capacity by including spare duct or tray space. Final routing design is subject to principal approval. Junction box engineering for accessibility and protection. Junction boxes serve as key interface points between field signal cables and multi-core instrumentation cabling. Their placement must optimize proximity to served instruments, generally within 15 to 20 meters, while ensuring location in low fire risk and electrically safe zones, or certified Zone 2 hazardous areas as required. Boxes should be constructed of stainless steel for field durability and fully equipped with mounting rails, terminal blocks, drain plugs, and gland plates. All cable entries must use bottom-positioned metallic glands to prevent moisture ingress. Cables entering laterally must be routed downward before entering, maintaining a drip loop. Terminal blocks for intrinsically safe circuits must be color-coded, light blue, and compliant with relevant safety enclosure classifications, e.g. XE terminals for non-IS circuits. Protection rating for enclosures must be at least IP65. All terminals must be secured against accidental loosening and incorporate mechanical retention or anti-vibration features. Where signal level classes 1 to 3 are present, terminal configurations must support functional shielding and separation of screens from armor or earth systems. Cable gland specification for environmental sealing and EMC compliance. Cable glands serve multiple critical functions: securing cable entries, maintaining enclosure ingress protection, preserving explosion protection ratings, and enabling reliable EMC bonding. For all electric signal cables entering field instruments or junction boxes, metallic glands must be used. These glands must provide circumferential 360-degree, low-impedance contact to connect the cable's armor or braid to the housing, effectively grounding and shielding against EMI. Glands shall be certified to relevant mechanical and explosion-proof standards with designs that comply with classifications such as XD or XE, depending on the enclosure rating. Acceptable designs include those conforming to BS 61121 1-1 type CDE or BS 61213 type CKEK, ensuring robust cable retention and electrical continuity. Gland positioning must avoid water ingress. Cables must always enter from below or drop below the gland before entry. Glands must not be installed at the top of instruments or junction boxes. Clamping or anchoring below the gland is required to eliminate mechanical stress on the seal. Special purpose glands are required where signal cables enter hydrocarbon-filled environments, e.g. rotating equipment sensors. These must block vapor migration while withstanding vibration and temperature fluctuations. Brass glands exposed to corrosive environments must be shrouded to prevent surface degradation. Glands intended for steel wire braiding, SWB, must specifically grip the braid, as standard clamping rings designed for SWA may not provide reliable contact. Improper practices such as connecting armor via pigtail wires, LITs, are prohibited, as they disrupt the Faraday cage effect and allow internal field exposure. Trunking and tray systems for mechanical routing and EMC shielding. Cable trunking and trays are primary support structures for routing both single and multi-core instrument cables in above-ground installations. These systems must offer mechanical protection, electromagnetic shielding, and accessibility for future maintenance or expansion. Closed metallic trunking is preferred over open tray systems due to its superior EMC performance. Where trays are used, U-shaped designs are acceptable, but ladder-type trays offer reduced shielding and must be limited to non-sensitive applications. All trunking and tray systems must be metallic and electrically bonded across joints and to supporting structures at multiple points using short, low-resistance connections. Supports shall be designed for expected load, spacing, and vibration. Internally, trunking must be free of sharp edges. Bolt heads must face inward, and cable exits must be fitted with protective grommets or bushings. Materials must be compatible with their environment. Stainless steel, galvanized steel, or painted mild steel are acceptable. However, galvanized components must not be used near stainless steel process equipment in fire-prone areas due to the risk of molten zinc-induced embrittlement during fire exposure. Trunking shall be side-accessible for cable laying and designed with sufficient clearance above to allow hand entry, typically 0.3 meters for narrow trays and 0.5 meters for wider ones. UV-resistant cable ties are required in vertical runs to prevent sagging or mechanical stress. Non-ferrous metals must be isolated from steel to prevent galvanic corrosion. However, insulating measures that interfere with EMC bonding are not allowed. Trunking and tray layout must provide at least 30% spare capacity for future cable additions. Typical layouts, such as those using 25 mm diameter cables, should reference pre-calculated trunking fill tables to determine allowable cable counts by width and height dimensions. Bends and branches must respect cable bending radius to avoid conductor damage. All layouts must be reviewed and approved prior to fabrication and installation. Underground trenches for cable routing and environmental protection. Dedicated underground trenches provide superior mechanical and thermal protection for multi-core instrument signal cables. Trenches must be designed with sufficient depth to avoid traffic-related damage and positioned above groundwater level where feasible to minimize long-term cable degradation. Routing must be marked with surface indicators and documented with cross-sectional drawings indicating layout, depth, and cable groupings. Signal cables in trenches may be laid without spacing for signal classes 1 to 4, optimizing space utilization. Where power or lighting cables intersect signal lines, crossings must be made at right angles with a minimum separation of 0.3 meters to mitigate electromagnetic coupling. Trenches must also avoid proximity to buried hot surfaces, such as uninsulated process piping. A minimum separation distance of 0.2 meters plus 0.1 meters per 100 degrees Celsius of pipe surface temperature is required to prevent thermal insulation degradation. The trench bottom must be leveled and limited to a slope not exceeding 10 degrees. Sharp directional changes must include smooth radii to comply with minimum cable bend tolerances. Where signal trenches pass under roads or other infrastructure, Protective ducts, DN100 or DN150, or reinforced concrete sleeves must be installed and sealed at both ends to allow future cable installation and prevent backfill infiltration. Trenches must be backfilled with screened sand, 2 to 5 millimeters grain, free of stones and chemical contaminants. A protective layer such as ceramic tiles or rigid plastic covers must shield the top cable layer from mechanical intrusion. Cable joining procedures for underground installations must be fully defined and approved, including materials, joint integrity testing, labeling, and inspection criteria. Special attention is required at building entry points, where cable support structures must be designed to accommodate long-term soil settlement. Transition structures or wall sleeves should be employed to prevent stress or mechanical fatigue at critical entry interfaces. Cable pulling and installation methods for integrity assurance. To preserve cable insulation and conductor integrity, cable pulling operations must be conducted in accordance with environmental and mechanical constraints. Pulling at ambient temperatures below 5 degrees Celsius is prohibited due to the risk of insulation cracking. All cable sections within a trench must be pulled in a single continuous operation. If interruptions are unavoidable, the trench must be temporarily covered with steel plates to prevent exposure or damage. Cables must be laid in unbroken lengths between termination points to avoid unnecessary joints, which introduce potential failure points. Construction teams must prepare drum allocation and takeoff schedules in advance to optimize cable utilization and minimize scrap. Slack must be incorporated into every cable run, especially at riser points or building transitions, to absorb differential settlement and thermal expansion. Cables must never be clamped to process equipment, piping, ladders, handrails, or structural steel. Instead, they should be supported via designated brackets, trays, or trunking systems. At each field instrument location, a service loop of at least 0.5 meters must be provided to allow ease of disconnection and reconnection during maintenance. For any installation involving signal cables entering enclosures with potential hydrocarbon exposure, sealed gland fittings must be used to prevent vapor or liquid migration along the cable path. To protect sensitive electronics, field wiring must not be connected to instruments until all welding activities in the area have been completed. Welding currents must not be permitted to flow through instrument ground paths or signal lines, as this can cause irreversible damage to internal components. All pulling, clamping, and routing operations must comply with the cable manufacturer's specifications regarding bending radius, allowable tension, and sidewall pressure. Noncompliance can lead to insulation breach, conductor deformation, or long-term performance degradation. Control room and auxiliary area cabling for secure termination and system integration. Control rooms and auxiliary equipment areas are central hubs for instrument signal management and must be designed to accommodate structured, safe, and maintainable cable routing. These areas typically utilize cavity floors, also known as raised access floors, which allow for concealed cable distribution while enabling segregation, ease of access, and system flexibility. Cables entering the building must pass through fire and water-sealed wall sleeves that meet EMC shielding requirements. The routing under the cavity floor must preserve segregation rules defined for safety, signal class, and functionality. Due to limited underfloor access, traditional tray systems are not practical. Instead, cables should be bundled and logically grouped using color-coded or labeled harnesses for simplified identification and maintenance. The cable entry design must reserve at least 20% spare space to accommodate future system modifications. Where auxiliary rooms are arranged in cellar-type configurations beneath control rooms, riser cabinets must connect cavity floors between levels, ensuring structural integrity and EMC continuity. All signal, power, and earthing cables must route through the cavity floor and enter cabinets from the bottom. Cabinets and racks must not be installed against structural walls to allow for ventilation, maintenance access, and uninterrupted cable routing. Cable gland plates are not required within these indoor enclosures. However, all cables must be securely anchored with low-resistance clamps or cable fixings to prevent movement, reduce strain on terminals, and maintain EMC performance. Signal marshalling is centralized in main distribution frame, MDF, cabinets. Each MDF is structured to include disconnect or test terminals for field cable termination, socket boards or terminal blocks for auxiliary room wiring via system cables, cross-wiring between field terminals and system connections to achieve logical marshalling. Thermocouple circuits require extension cabling all the way to the point of cold junction compensation, typically the input card of the receiving device. The correct polarity and cable type must be maintained throughout the run. Instrument cabinets must be configured to accommodate full signal capacity, including designated spare channels. Modular system cabling between instrument cabinets and MDFs ensures standardized terminations and minimizes installation errors. The instrument cabinet design must reserve at least 20% spare I/O capacity for operational flexibility and future expansion. Earthing and bonding for personnel safety and signal reliability. Effective earthing and bonding are essential for protecting personnel, ensuring the reliable operation of instrumentation systems, and maintaining immunity from electromagnetic interference. Two distinct earthing systems must be implemented and clearly separated: the safety earth, which protects against electric shock and equipment faults, and the instrument earth, which provides a low noise reference for sensitive signal circuits. Each instrument cabinet and MDF must be connected to the instrument earth bar via a dedicated color-identified cable with a minimum cross-section of 6 mm squatters. Terminals for these connections must use yellow-black insulation and be clearly marked with the associated cabinet or MDF number. All earthing bolts must be a minimum of 10 mm in diameter to ensure mechanical integrity and low resistance contact. Some equipment manufacturers may specify maximum allowable resistance to earth or require isolated earthing. In such cases, these requirements must be followed precisely, and documented verification must be provided during commissioning. Earthing connections for signal cables. Instrument signal cable screens must be earthed using the star point method, ensuring that each screen is connected to instrument earth at one and only one location. Screens must be electrically insulated from cable armor, equipment enclosures, and support structures to prevent ground loops. For screened field cables running between junction boxes and MDFs, the screen must be earthed only at the MDF. At the field end, the screen should be insulated, left unconnected, and kept the same length as the signal wires to enable future integrity checks or continuity testing. Cables routed directly from the field instrument to the receiving equipment, bypassing junction boxes and MDFs, must have their screens earthed only at the receiving end. Screens within control room or auxiliary system cabling must also be connected to instrument earth at the MDF only. Where screened cables connect two MDFs or two instrument cabinets, the screen must be bonded at only one end to maintain the star configuration and minimize circulating current risk. Safety earth bonding for armoring and enclosures. All metallic armoring, SWA, braiding, SWB, and conductive sheathing must be bonded to the safety earth at both ends of the cable. Instrument housings, junction boxes, local panels, and cabinets must be bonded to adjacent trunking or structural steel through dedicated bolts and metallic contact interfaces. Use of serrated washers or shark rings ensures reliable low-resistance contact, even under vibration or thermal cycling. Field-mounted enclosures must include accessible earthing bolts. Any external earth connections must meet relevant safety and explosion protection standards and be mechanically protected from corrosion and physical disturbance. Earthing of intrinsically safe circuits. Safety barriers and galvanic isolators used in intrinsically safe loops must be connected to the safety earth unless a manufacturer-approved dedicated earth is specified. Earthing must be secure, direct, and capable of handling potential fault currents without exceeding resistance thresholds that could compromise intrinsic safety compliance. Earthing of cavity floors for control room safety. Cavity floors in control rooms and auxiliary buildings must be fitted with a 1.2 meters by 1.2 meter earthing grid constructed from bare copper stranded wire, minimum 16 millimeters cross-section. This grid must be bonded to the main safety earth ring at intervals not exceeding 5 meters. The mesh ensures equal potential distribution and provides a low impedance return path for any stray or fault currents, enhancing personnel protection and equipment resilience. Sharp lightning protection for instrumentation systems. Instrumentation installations in industrial facilities are inherently vulnerable to direct and indirect lightning strikes, especially when mounted on elevated structures or in exposed environments. A comprehensive lightning protection strategy must be implemented to ensure continued functionality of field instruments and signal transmission systems without compromising explosion protection standards. All lightning protection measures must be compatible with hazardous area classifications and shall not interfere with flameproof AXD, increased safety XE, or intrinsically safe AXI protection concepts. Measures must be reviewed and approved during the design phase to ensure coordination with structural lightning protection systems and plant-wide earthing arrangements. Protection for instruments and cabling in protected areas. Wherever possible, instruments and associated cabling should be installed in areas shielded by earthed structural steel or dedicated lightning protection systems. These protected areas reduce the likelihood of direct lightning strikes. When standard practices are followed, such as using twisted signal pairs, properly shielded and armored cables, and verified earthing, no additional lightning-specific components are typically required for installations within these zones. Routing cabling alongside grounded steel structures or pipework further attenuates induced voltages from nearby lightning events, enhancing the effectiveness of passive shielding and minimizing transient coupling. Protection for instruments and cabling in exposed areas. For instruments installed in unprotected locations, such as tank farms, tower tops, or elevated pipe racks, supplementary lightning protection is mandatory. These installations must be identified during the detailed engineering stage and equipped with surge protection devices at both ends of the signal path. Protection is required whether the threat is direct, e.g. elevated sensors, or indirect, e.g. cable runs across open terrain. Surge protection devices must include a combination of gas discharge tubes, metal oxide varistors, MOVs, or fast clamping Zener diodes to safely divert high-energy transients to ground. Devices must be selected based on system voltage levels, response time, and clamping characteristics, and they must not incorporate fuses or slow-reacting elements. Field instruments connected to long cable runs or serving as remote nodes, e.g. tank-level transmitters, telemetry units, or distributed multiplexers, may require built-in lightning arresters or external surge protectors as specified by the instrument manufacturer. Preferred communication mediums for lightning-prone installations. For long-distance or interbuilding communication lines, particularly where routing through lightning-exposed zones is unavoidable, fiber optic cables are preferred. Optical fibers offer complete immunity to electromagnetic induction and lightning transients, and their dielectric properties eliminate the risk of introducing dangerous voltages into protected systems. Where copper-based communication is used, galvanic isolation must be employed at both ends of the circuit to minimize the propagation of induced voltages and to protect sensitive electronic interfaces. Shield continuity and correct earthing practices remain critical to maintaining system integrity under surge conditions. Pneumatic tubing for signal transmission and field integration. Pneumatic signal transmission remains a reliable option for certain control systems and final elements, particularly where electric circuits are undesirable or intrinsically safe environments are difficult to maintain. Pneumatic tubing must be designed and installed to maintain signal pressure integrity, resist mechanical damage, and facilitate future maintenance or expansion. Single tubing runs connect field instruments, such as pressure controllers or pneumatic transmitters, to junction boxes. From there, multi-core pneumatic tubing routes signals back to the main distribution frame, MDF, in either the central control room, CCR, or a field auxiliary room, FAR. Routing must prioritize low fire risk zones and avoid congested or high temperature areas. Above ground installations are acceptable with principal approval where cost savings or local standards justify their use. Underground routing offers better fire and impact protection and should be used where practical. Design must accommodate 10 to 15% spare capacity in all multi-core tubing installations to allow for future instrumentation upgrades or reconfiguration. Any pneumatic lines serving emergency shutdown, depressurizing, or fire protection systems must be routed and protected with the same rigor as electric safety-related cabling, ensuring performance during fire or seismic events. Tubing selection for service conditions and material compatibility. Tubing must be selected based on environmental exposure, signal pressure range, chemical compatibility, and routing configuration. Tubing cores shall have an outside diameter of either 6 millimeters or quarter inch based on system standardization. Both polyethylene PE and copper options are widely used depending on the installation type. Indoor, field cabinets panels, PE, black, unarmored for general use, bare copper for premium durability or EMI resilient environments. Outdoor, above ground, copper with black PVC sheath for mechanical and UV protection, PE with PVC oversheath for weather resistance. Outdoor and underground, PE tubing with PVC and lead sheathing or equivalent for chemical resistance and moisture barrier. Lead may be replaced by other sheathing material, provided it meets the same protection standard. All tubing must comply with specified standards for flexibility, pressure rating, flame retardancy, and environmental durability. Material selections must consider resistance to UV radiation, corrosion, hydrocarbon exposure, and mechanical abrasion. Junction boxes for multi-core pneumatic tubing. Pneumatic junction boxes provide a consolidation point between field devices and multi-core tubing bundles. They must be installed in accessible low fire risk areas and located as close as possible to the connected instruments to minimize single line lengths, ideally not exceeding 15 to 20 meters. Tubing shall enter the junction box through adapter plates fitted with proper strain relief. Where a transition from plastic to copper tubing is required, it must be performed using bulk connectors securely mounted on the side walls of the junction box. Angle-type bulkhead fittings are preferred when directional changes are needed, as they reduce stress on tubing and simplify installation. Boxes must provide internal support and clear identification for all terminations to ensure easy troubleshooting and future expansion. Sealing and mounting hardware must be corrosion resistant and compatible with the selected tubing material. Installation best practices for pneumatic systems. All pneumatic fittings must be of the compression type and compatible with the tubing diameter and material. Brass and engineered plastics are acceptable, subject to pressure and temperature ratings. Fittings shall be selected based on reliability under vibration and thermal cycling, especially in outdoor or high-traffic areas. Where tubing exits trunking systems, bulkhead unions must be installed to preserve enclosure integrity and prevent tubing strain. In cases where the tubing serves instruments without an air supply, e.g. direct-acting control valves without boosters, the tubing must be rigidly clamped to a 25 mm dummy pipe or steel angle iron mounted to the structure, preventing sagging or accidental damage. All installation work must ensure proper bend radius, protect against kinks or crushing, and maintain accessibility for leak testing or replacement. Tubing routes should avoid hot surfaces, sharp edges, and potential impact zones, with additional mechanical shielding applied where necessary.